Recording in progress.
Hi friends, in this lecture I am going to discuss what is self-energy. Under this heading I am going to discuss first one, electric potential energy of a uniformly charged thin spherical shell, and second one, electric potential energy of a uniformly charged sphere. Now see the first one, it is uniformly charged thin spherical shell. Okay, let us see what is self-energy first. Right. So first we are taking here a thin spherical shell. A thin spherical shell. You can take it as Caesar, and we want to charge this one. Initially, this was uncharged. We want to charge this body. Let us say we want to provide a charge Q. Okay. So first we focus here. What is the meaning of a self energy? Initially, this body was having no charge. So now we are providing a charge. Means we are charging the body. So in the process of charging the body, work will be done, and that work stores in the form of potential energy, which we are calling as a self energy. I am repeating, when we are charging a body, its meaning is bringing charge from infinity up to this point, becomes up to this body. In the process of this, work will be done, and that work stores in the form of potential energy. And this is what we call self energy. Let us see how we are calculating that. So we want to give a charge finally capital Q. Let us take at one instant, charge on the body is a small q. So initially charge was 0. We are now bringing small charge dq from infinity and keeping on the surface. We are bringing small charges from infinity and placing on the surface. Let us take at one instant, charge on the body is small q. Okay. Now at this instant, potential of the body, it will be equal to kq by r. This is the potential of the body at that instant when charge is q. Now we are bringing an extra charge dq from infinity and placing on the surface. I am repeating, I am bringing a charge dq. It is a very small charge and placing on this one. So like this, we are bringing small charges and placing on the surface of the thin shell. Okay. Now you can see between this existing charge and this coming charge, there is a repulsion. Because of this repulsion, we have to do work in bringing this charge. Because of this repulsion, we have to do work against that repulsion in bringing the charge. So that work now stores in the form of potential energy. And that work equal to, we can say charge dq into potential difference. So we are bringing from infinity where potential is 0, and here potential is V, that is V minus 0. So this is now work done in bringing a small charge dq, charge into potential difference. Like this, we have to bring all small charges until the charge becomes here capital Q. Initially charge was 0. This is a final charge. Let us take this as small work done, that is dW. Okay. Now see how much work is done. W equal to integral V dq. So what is this? This is work done in bringing a small amount of charge dq from infinity up to the surface. Okay. Now we have to integrate. So it is from where to where? It is from charge q equal to 0 to it is up to capital Q. So this is work done by external force, right? Now substitute the value of V here. So V value KQ by R. Here K stands for 1 by 4 pi epsilon naught, okay, into dq. So here why we are taking integration? Because when we bring dq from infinity to up to here, work is done. Next, we bring one more dq charge from infinity up to here. So like this, while charging the body, work is done. That work is now what we call self energy. Okay. Now see here, K constant, R constant, take both outside. Remaining is now integration of Q dq. It becomes now Q square by 2, right? And take limits. So Q square by 2. That is now work done in charging the body. And this work stores in the form of potential energy. This is what we call self energy. Or we can say it is the electric potential energy of that thin shell which is uniformly charged. Okay. So final result is kq square by 2r. Let us now discuss same thing for a solid sphere. So here we have taken charges only on surface. Okay. This is a thin shell, charges only on surface. But we are taking here. So now we are taking as solid sphere and charges now in the entire volume. Charges in the entire volume. So this is for thin shell. Okay. Thin shell. Now we discuss solid sphere where distribution of charges in the entire volume. It is a solid sphere. Right. See what we are doing here. So we are having charge now in the entire volume and distribution of charge is uniform. Distribution of charge is uniform. Okay. So now charging this body means initially no charge. Now we are bringing charges, small dq charges from infinity and placing now in the entire volume. Placing in the entire volume. So finally, charge in this charge is in the entire volume and distribution of charges uniform. So in the process of bringing these charges, work is done and that work stores in the form of potential energy. Now see how this is, how to calculate this one. Let us take this solid sphere as a combination of thin spherical shells. This is taken as combination of thin spherical shells. Students, if you remember, we have taken the same kind of logic in rotation, right? While taking calculation for moment of inertia of solid sphere, we have taken it is a combination of thin spherical shells. Okay. Let us take total charge Q, which we want to place. Let us equal to R. Now assume for this spherical shell, radius is smaller, its width equal to dr, So assume at one instant we are having a sphere, solid sphere of radius smaller. I am repeating. Assume at one instant we are having a solid sphere of radius smaller. Now we want to bring some extra charge so that its radius changes from r to r plus dr. It changes from r to r plus dr. I am repeating. Assume that at one instant we are having a solid sphere of radius small r. Now we want to increase this radius from r to r plus dr by adding charge. Okay. And we can see charge now in this volume. Charge now in this volume. I will mark that volume. Charge in this volume. Charge in that volume. See how much it is. So again, same process we are going to take here. Work done is equal to integral see what is now potential of this sphere. Okay, sphere of radius is small r. Okay, that is now potential is kq by r, where q is charge of this small sphere, and we are bringing now extra charge, that is now dq. How much? We are bringing extra charge dq from infinity to place on the surface of this solid sphere. Okay. Then see extra charge will be 4 pi r square into dr. That is now volume of this part. Okay, volume of this part is how much? 4 pi r square into dr. Okay, into density. Density is now rho. Okay, where rho equal to, I am writing here, where rho equal to total charge is q. Q upon volume is 4 by 3 pi r cube. That is rho. Okay. Now see calculation part. Integration of k by small r. In the place of q, I am writing here. Q by r cube into r cube. Okay. See how we have taken this. Charge is now proportional to volume, right? So here volume how much? 4 by 3 pi small r cube. Okay. And total volume is 4 by 3 pi capital R cube. So in the place of q, I am writing here, in the place of q, I will write here in the place of q, q equal to rho into 4 by 3 pi r cube. Okay. In the place of rho, take this value, 4 by 3 pi gets cancelled. Remaining is now q by capital R cube into small r cube. Okay. So k cube by r into 4 pi r square into dr in the place of rho. Now substitute this value, that is q by 4 by 3 pi r cube. Okay. Now simplify this and see what we get. 4 pi and 4 pi gets cancelled. So here 4 pi and here 4 pi gets cancelled. Next, See what else left. What else left here? I can take here k q square by k q square by k q square 3 also there, 3 also there. So 3 here, 3 k q square. Remaining is now r cube, and this is r cube, r power 6. R power 6. I'm taking constants outside. See what else left here. R cube, r square, r power 5 dr, right? R power 5 dr means it becomes now, wait, it is r square, and this is now r cube, and this is now r square, right? R power 5. Integration of r power 5 dr. Then see what we get. And one more thing I have not taken. See, one r gets cancelled here. So remaining is only integration of r power 4, right? dr, right? Now this is equal to r power 4 dr becomes r power 5 by 5. So this is equal to 3 by 5 k q square by r. That is now self-energy of a solid sphere. That means charge is now in the entire volume. Charge is in the entire volume. So self-energy of thin shell k q square by 2, or self-energy of solid sphere 3 by 5 k q square by r, right? Let us see now how we use these two while solving problems. Okay. Suppose a question is given like this. This is one thin shell. Okay. This is a thin shell. Charge is taken as a Q1. Radius is R1. Okay. And here I am taking solid sphere. Charge is a Q2. Radius is R2. Okay. Radius is R2. Let us take now separation. So this part without having confusion, okay? Right. So we are given here one thin spherical shell. Radius is R1, charge Q1. It is now solid sphere, means charge is now in the entire volume. Charge Q2, radius is R2. And between these two separation is, take it as small r. Okay. From center to center. Now question is, find potential energy of the system. What is it? Potential energy of the system. Then we are taking potential energy equal to their self energies for thin shell k q1 square by, it is a k q square by 2r. So k q1 square by, it is a 2r1 self energy of that thin shell. Next, self energy of the solid sphere, that is 3 by 5 k q2 square by r. Apart from these two, because of interaction between these two, okay, that means there is now interaction between the thin one and solid sphere. Because of the interaction, there is a potential energy. Generally we are calling as interaction potential energy. These two are self energies. Now we are taking interaction potential energy. Then what we are doing is, we are replacing these two with the 2 point charges at their center of masses. I am repeating, We are replacing both the bodies with 2 point charges Q1 and Q2. And between those 2 point charges, separation equal to small r, which is nothing but separation between their centers. Okay, that is now potential energy for 2 point charges K, Q1, Q2 by separation between them. This is now potential energy of the system. So self energy, and interaction potential energy. Okay. If you see for point charges, there is no self energy for point charges, right? Like this, we can use while solving problems.